Okay guys, good morning to you all. Lab this week we'll meet upstairs. Bromination of transtylbene. Any questions about lab this week? We should be getting to stereochemistry today. We need to finish up alkene reactions. Green sheet, we're down to letter B. I'm sorry, not letter B, next page, letter C. Other reactions of alkenes. Before we proceed though, any questions about alkene reactions? Any questions about alkene reactions? How are we doing with the alkene puzzle? Any questions at all? Okay, let's proceed. Letter C, hydrogenation of alkenes. Shown here, this is a picture of a hydrogenation apparatus where we use hydrogen gas. Back over in the white sheet, white handout. Here we have the reaction that we're looking at. To take an alkene, we can react it with hydrogen, H2. And we will add hydrogen across the pi bond. We'll end up with a hydrogen on each carbon. Okay? When we do this, the alkene now becomes an alkane. Very simple. The two H's are there. There's one UH here, one UH here. They're not shown though. This is called a hydrogenation. We're adding hydrogen to the alkene. Very easily done. It's also called a reduction because anytime you add hydrogens, it's called a reduction. We said that last time when we used sodium borohydride. So we can reduce the alkene It does require a catalyst though, a precious metal catalyst. Precious metal, not a base metal like iron or zinc. Precious, expensive, like palladium, platinum, nickel, which is semi-precious, rhodium. Okay, your choice, not all of these. One student said one time, have all these. No, one of these. Palladium and nickel are probably the most common. Very important. The reaction pretty much does not work without the catalyst. In terms of regiochemistry, there is no regiochemistry. You put an H here and an H there. We can flip it around and put an H here and an H there. No difference. There's no regiochemistry. There will be stereochemistry, for example, in the example over there. Mechanism for this. It is not an ionic mechanism. What's an ionic mechanism? One that involves ions as intermediates. Just about every mechanism we've looked at, probably all of them have involved ions as intermediates. Thus, every mechanism we've looked at thus far has been an ionic mechanism. This is not an ionic mechanism. Mechanism is shown at the top. It is not well defined. We will not be using any arrow movement. We just sort of look at it a little bit so it's not entirely magic. The alkene, the pi bond particularly, approaches the metal face. Okay, these are like the metal atoms. Metals are known to absorb hydrogen gas. How do they do that? Well, that's not well defined either. But there's an interaction between metals and hydrogen, and lots of other type of gases. what we know here and how this is presented is the hydrogen sort of coordinates with the metal, and it's almost like it breaks the hydrogen bonds. Again, a little bit nebulous, okay, what's going on here. Then the alkene approaches this face, and it's almost like these hydrogens become darts. Very scientific. And they're shot into the pi bond, boom, 1 H on each carbon. You want more information, right? I know you do. Well, look in your book. You're not going to find much more. Okay? It's not a well-described mechanism. What we do know that is there's no intermediate. There's no intermediate here. There's no ionic intermediate. The alkene is not polarized and the pi bond attacks it and leaves cation. No, none of that. There's only a single transition state. The H's come from the metal. They're shot into the pi bond. And we end up now, when we added 2 H's, these 2 carbons now become tetrahedral. We now have an alkane. And we've reduced our alkene to an alkane by adding 2 H's by hydrogenating. The metal surface is as it was at the beginning, so it's no change in it. It's a catalyst. Because the hydrogens come from the metal surface, it is a syn addition of the H's. That is, here's the pi bond. Here's the metal with the 2 H's. Okay. Have your hydrogen blasters ready. Okay. Here's the pi bond walking down the road and make the bonds. Boom. Okay, they came from the metal. The 2 bonds, are they the same side or opposite sides to each other? They're the same sides because they came from the metal. They're both over here. Unless one bond's going to be here and the other bond comes around. No, they both come from the metal. And so the 2 bonds come in the same side. That is syn, not anti. Same side addition from the metal. We can go back over here and look at things like this. Hydrogenation of either one of these alkenes. Nomenclature, how are we doing? What's the name of this compound? 1, 2, 3, 4, 5. What is that? 1-pentene? Is 1-pentene stereogenic? Of course not. No. What about this? What's the name of this compound? 2-pentene. Is it stereogenic? Certainly it is. Yes. You should know all that. Any questions about nomenclature? If you have questions, let's try again on Friday. Questions about nomenclature. Either one of these compounds, these have the same formula. What type of isomers are these? Constitutional isomers that have different connectivity. You can tell that from the name because they have different names. Either constitutional isomer, if you hydrogenate it with hydrogen and a metal catalyst such as nickel, either one gives the same compound, pentane. You should see that. They both give the same product if you hydrogenate. Question though, which route is more exothermic? Which route to pentane is more exothermic? Based on my question, I'm telling you that both routes are exothermic. I'm asking you which is more exothermic. First off, does it make sense that this reaction is exothermic? We can pull out our calculator. But how can we tell that from just looking at the reaction that it should be exothermic?
One pi bond breaks, 2 sigma bonds.
One pi bond is being broken, 2 sigma bonds are being formed. A weak bond is being broken, 2 stronger bonds being formed. Again, you can pull out your calculator and look at some bond strength tables and you'll get exothermic. But which one is more exothermic? We should also be able to do that by just looking at what's going on. Which one's more exothermic? How would we do this? How would we figure this out? Anybody? Which one gives off the most heat? Yes.
Would it be the first one because it's least stable?
Least stable compared to this.
Yes.
So you look at the stability or the energy of your starting materials. Which one is higher in energy, A or B?
I thought A.
So A is higher in energy. Why is A higher in energy?
Because it's not as stable.
Alkene.
That's just the same question. Why is it not as stable? I think you know the answer. I'm just trying to get you to say it out loud so everybody can hear it.
Because it's on the side rather than in the middle, the pi bond.
Because it's monosubstituted as opposed to disubstituted?
Exactly.
Is that the terminology you wanted to use? Yes, and we covered that, right? They are otherwise isomers. More stable. Okay? They're both going to the same place. That has a certain stability. Right? I bet it ain't gonna. Let's see here. If this is A and this is B, we can put A here. B would be lower. A here, B lower. They're going to C. How does C compare to these two? It's more stable. It's got stronger bonds. That's what we said 2 minutes ago. C would be down here. A goes to C with just a transition state. B goes there with just a transition state. Which one's more exothermic? Doesn't matter anything up here. The exothermic comes from here. This one is here to here, and this one is here to here. Right? There to there versus there to there. Which one's more exothermic? A to C, right? And going from A to C, you would give off more energy. These things should be pretty straightforward if you just make it easy. Okay, a little stereochemistry over here. If you hydrogenate this alkene, hydrogen, palladium, or carbon, a lot of times the metal is dispersed onto carbon, charcoal. That gives it more surface area. Because you don't want to use much palladium. Wee little bit, you know, like a grain of salt. You put a grain of salt in a big old pot, it's just going to be a little bit there. How can you spread the grain of salt out? Well, maybe if you grind it with charcoal, then put it in there, it'll be more spread out because it's all in that charcoal. Okay? Very common to have like some type of sort of inert solid to help spread out the palladium. The alkene has stereochemistry. See, this alkene had no stereochemistry. We're going to learn, you should see that, obviously. But once we get going to stereochemistry, we have to know. This alkene does. We've looked at this before. On the ring, cis or trans is possible. That's stereochemistry. Are you going to get cis or trans here? Well, you're going to get cis only. Why? Because when the H's come in, they come in from the same side, correct? The H's are on the same side. You're drawing the H's. See how they're on the same side? Because that's how they came in. But you'll also get the enantiomer. The enantiomer will be just the opposite. It will be where this is back, the ethyl is back, and the methyl is back. It's also cis, okay? But it's the enantiomer. It's the mirror image that's different. So this reaction is stereoselective. Stereoselective hydrogenation of an alkene. It's stereoselective because it's a syn addition of hydrogen. Before we turn to the next page, remember fatty acids? Very top is a saturated fatty acid. These come from natural fatty acids that you find in like olive oil. Those are more natural. Saturated fats are not that natural. They're synthetic, man-made. How would you convert this compound to the one above? What do we need to do? What do we need to react it with? Yes, just hydrogen. And what else you want to use? Your choice. Nickel. Because the difference is, somewhere between two of those carbons, we got to add another H, another H. Every one of those carbons has two H's. CH2, CH2, CH2. But these two carbons only have one H. Hopefully you can see what's going on there. If not, you just look at it until you see what's going on there. It's just a hydrogenation. The monounsaturated fat is hydrogenated. You've heard of hydrogenation, right? Hydrogenated fats. That's what we're doing. One of the problems is when you hydrogenate, you get saturated. Sometimes, though, you can, in this process, you can convert these to transalkenes. Because the reaction can be reversible, and when it reverses, it tends to go back to trans instead of cis. But we won't go into that. But that's how you end up with transalkenes, because the hydrogen's coming back out, and coming back out as a cis form. As a trans form. Okay. Take a page over here. Well, the top here is what we just looked at here, except it has 3 examples. All these alkenes up here are constitutional isomers, all with one pi bond. If we reduce them by hydrogenation, they all go to the same place. They do. They all become the same alkene. Which reaction gives off the most heat? Well, it'll be the first one. Delta H is more negative, because that's a mono substituted alkene. That's a di, and that's a tri. These are a little bit condensed, so it's a little bit tougher to see and if it's drawn out completely, but you got to look at it. More stable, less energy when it comes down to the same place. That's what we just described with the ABC. This is called the heat of hydrogenation. H of H. H of H. Which one of these reactions has the greatest heat of hydrogenation? This one. Greatest heat of hydrogenation means it gives off the most heat. Heat of hydrogenation is the heat that's given off. This one gives off the most. You've got to be careful though, because this is the most negative delta H. So that sounds like the lowest number. Yeah, it's the lowest number in terms of delta H, but it's the greatest amount of heat given off. And that's what H of H refers to. So make sure you understand what an H of H is. The first reaction has the greater H of H, because it gives off the most heat. It gives off the most heat of hydrogenation. Question, which alkene will have the highest heat of hydrogenation, left or right? They're both disubstituted. Can we distinguish between them otherwise? Yes, they're both di, but what's the difference? Yes, one's cis, one's trans. Which one's most stable? Trans is most stable. Just like when we do in conformers. Which is most stable, syn or anti? Anti. But I can rotate. These can't rotate, so they're stuck like that. But you can still say which is more stable. Big group's opposite, more stable. So which one has the highest heat of hydrogenation? This one, because it sits higher. When they're hydrogenated, they both become what? Hydrogenation of either of these compounds produces what compound? No trick. It's overly... What's the name of the compound when these are hydrogenated? Do what? Propane? There's 4 carbons. Do what? What's the name of the compound produced when either one of these is hydrogenated? Okay, we need to back up a long way. First off, nomenclature of alkanes. 4-carbon alkane is a... Okay. You know what these produce when they're hydrogenated? Which reacts faster with HBr, left or right? Before we move on, let's look at a couple of miscellaneous questions. Sort of in the same line as this, but obviously different. Let's go back over here. Which of these reacts faster with HBr? One of them reacts 100,000 times faster. Which one reacts faster? Down here, both get the same product. Which reaction is faster? Which reaction is faster? Anybody got this one?
Is it the top is mono-substituted?
The top is mono-substituted? No, this alkene is di-substituted. Huh?
Would it be the bottom
Why do you say this one's mono-substituted?
I thought it would only form on the tertiary, not on the end. Oh wait, never mind. This is I was wrong.
But this is not a mono-substituted alkene, it's a di-substituted alkene. Which reaction is fastest? Examples of hydrogenation. Here's a synthesis of Propecia. Used to treat hair loss. It's also basically the same compound that's used to treat BPH. In the synthesis of Propecia, right here we have a hydrogenation. Going from 43 to 44. This alkene is being hydrogenated. And so now we have H added to each carbon. It's now saturated here. They're using hydrogen. They're using platinum oxide. You can also use salts of these metals, oxides, Platinum metal is produced sort of in situ in the reaction. Interesting that they have to heat this. It is a pretty crowded reaction site, maybe that's why. But there's an example of an alkene hydrogenation. Note that the carbon-oxygen double bonds are not hydrogenated. And we saw that in the fatty acids. The acid carbonyl was not hydrogenated. Only the carbon-carbon double bond is hydrogenated. Sometimes you can hydrogenate the CO double bond. It's much more difficult. Typically at this level, you're pretty much not going to see it. Except if it's benzylic. You'll see that in organic too. So ultimately, to make this molecule here, Propecia, which looks a lot like some of the hormones. Next page. These are a lot of the human hormones. You'll learn these in biochemistry. Ultimately, these can be made from cholesterol in your body. Okay? Don't ever let somebody tell you don't need any cholesterol. You gotta have cholesterol to exist. Make all these hormones like testosterone. All right? Cholesterol. Although your body can make its own cholesterol. Here's testosterone. Testosterone in the body, particularly the male body, is reduced to DHT. This alkene is reduced. H is added to each carbon. So 2 H's have been added. Because 2 H's have been added, this is called dihydrotestosterone. 2 H's testosterone. All right? 2 H's have been added, DHT. Now your body does this not with hydrogen and nickel, but with enzymes like 5-alpha reductase. Okay? Different mechanisms than shooting hydrogens from the metal. All right? Amazing enzymes. Now DHT has high activity in the male hair follicles and prostate. And the activity is a bad activity. Okay? Too much of this leads to bad things in the hair follicle. It makes the hair follicle become less active, etc. Thus, we would like to limit the amount of DHT formed in the body if you want to limit hair loss and prostate problems. This can be limited by inhibiting this enzyme, 5-alpha reductase. If we can stop this enzyme from acting, we can stop this from forming. A lot of drugs focus on or target this enzyme. Those would be called 5-alpha reductase inhibitors, used to treat male pattern baldness and BPH. One of these 5-alpha reductase inhibitors was shown on the previous page. It's known as what? Propecia, yeah. Propecia is a 5-alpha reductase inhibitor. You look at the similarity between Propecia and DHT. Propecia interacts with the enzyme, keeping testosterone from interacting with the enzyme. Okay? But ultimately, it's stopping that hydrogenation reaction. But your body doesn't use hydrogen. Question?
Why did they draw in the hydrogen on DHT and Propecia?
They drew in one of them.
Right. Why?
Because the carbon that it's on is chiral. Excellent question. And when you have a chiral carbon, you then have choices. And so if you have choices, it's important to clarify. For example, if I told you my factory produces hands, you might wonder, does it produce right hands or left hands? I could say, well, it produces both. Or maybe my factory only produces right hands. And so maybe when I show a hand, I want to make sure I show a right hand. You have choices. At the other carbon, it's not chiral. So it doesn't matter. So that's why I wasn't shown on the other carbon. We got to know when it's important to show stereochemistry and when it's not. Great question. That's exactly where we're heading. Okay, there were a couple of questions in there that I don't think we were prepared to address. So we'll try again later. Okay, those are your alkene reactions. Yes.
So how does pressure come into play with all of that? With all of the hydrogen?
Well, hydrogen's a gas. And first off, I showed the apparatus. You've got to be able to pump the gas in. Typically, it's done under pressure. I mean, it could be atmospheric pressure, but a lot of times higher pressure just makes the reaction occur easier.
Okay, so it doesn't affect the structure at all when it's reacting? It's just
No, pressure, no, I mean, you're still going to get the same outcome. We've discussed all the outcomes.
Okay.
Some alkenes are more difficult to hydrogenate than others for reasons that we're not going to be looking at. Typically, you do give it a little pressure. That's almost out of just convenience and necessary. I mean, you just put hydrogen in and it's going to create pressure.
Okay.
And so it's good to know how much. I mean, your water heater at home outputs water at a certain pressure. But does it really matter? No, you're still able to take a bath. It only matters if it's so low that your water doesn't run.
Okay.
Then you worry about low pressure. Okay, any last questions about alkene chemistry? We should have a quiz pretty soon over everything up through alkene chemistry. Time for stereochemistry. 3 main topics for test 2, alkene chemistry, stereochemistry, and then we'll also do alkyne chemistry. Alkyne chemistry will be shorter because a lot of those reactions are similar to alkene. But because alkynes have 2 pi bonds, it'll just be twice the fun. Okay? Stereochemistry. Stereochemistry began back in the early 1800s, or when it was first recognized. I'm sure it began many, many years before then, like in nature. But Louis Pasteur was one of the first to recognize stereochemistry when he was dealing with tartaric acid. And he noticed that tartaric acid that came from natural sources, like maybe grapes or some other fruits, it had a weird property of rotating polarized light. But tartaric acid that was made in the lab, and they could do that at that point, tartaric acid made in the lab did not rotate polarized light. So there was something different between the samples. And there's something different between the inherent structure. Now that doesn't mean that things made in the lab versus things made in nature are not the same. They can be the same, but in this case they were not. It all comes down to the chiral carbons here. And the end story is the tartaric acid that came from nature was chiral. It's like with hands. We'll talk about hands. 2 hands. In nature, the tartaric acid that's made is only like all right-handed, or all one. But when it was made in a lab, they produced both hands. And the mixture would not rotate the light. But the stuff from nature, which was just one hand, it would rotate the light. Now I wish we had ample time to talk about history and to go from there to what we know today and to build a story. But we don't have time, though. I would love to have that time. That's where you have to do reading if you're interested. I would look on Wikipedia. Look up chirality on Wikipedia. You'll find all the history. Began back then, Louis Pasteur. And then a Dutch chemist named Van Hoft proposed a reason for this. He proposed chirality and the tetrahedral nature of carbon, and that's why it all comes from, the tetrahedral nature of carbon. But let's get into it. Everybody got the handout? I sent you one by email, Stereochemistry warm-up. Types of problems we'll be seeing. And then I gave you one last time, right? That's our outline. Okay, chirality. There's a big paragraph up there. That's sort of my overview of it. Let's start with the R and S enantiomers of 1-bromo, 1-chloroethane. And when I say enantiomers, that's like me saying hands. This is a pair of enantiomers, the right hand and the left hand. What's the relationship between my two hands? They're the same, except they're mirror images. If that looks in the mirror, it's going to see this. They have the same connectivity. I've got a thumb next to a pointy finger. Well, this one does too. Thumb next to a pointy finger. It's the same connectivity. It's just somehow just all inverted, or it's all opposite. It's a mirror image. These are enantiomers. That's what enantiomers mean. Now we call this the right hand and the left hand. You've known that since about 4th grade, right? Or earlier. Compounds we call things like R and S. It's the same idea. Let's look at the enantiomers of 1-bromo, 1-chloroethane. Let's see. What do we got here? There's ethane, 1-bromo, 1-chloroethane. Is that it? Yes. This carbon here, first off, it's tetrahedral. What else is on this carbon that's not drawn? There's one H there. sp3. The groups around this carbon are all in a tetrahedral manner. We need to draw that better. Right here, there's no stereochemistry shown. And it's very typical to not show stereochemistry. But if you want to talk about it, you've got to be able to show it. And then you can draw a more advanced or more accurate structure. This carbon is known as chiral. Okay, I usually star them. Chiral. A chiral carbon. A chiral carbon is one that has no symmetry at the carbon. No symmetry. And we use a fancier word, asymmetric. No symmetry at this carbon. Symmetry you can tell by looking, does it have a line of symmetry? Can you come right between it? Let me change one of these bonds to green. And before we start drawing, let's look at this symmetry. Well, maybe we should go back to see where we're at. Let's do this first, because we got to orient you guys. Let's draw the two enantiomers of this. Let's see. We got bromine. boom. Here's our, here, we're going to make this the carbon. But let's make it tetrahedral. Let's put the chlorine forward. We could put the H forward, but I put the chlorine forward. Let's put the H thus back. Now we're showing stereochemistry of this compound. We can also do a mirror image of this. The mirror image, let's draw it as a mirror image. If this was a mirror that it was looking into, what would it see over here? It would see that. Do those look like they're mirroring? Does that look like mirror images? Here I am. I'm the molecule. Chlorine. Let's do it here. I need to go back to boom, boom, boom. Okay, carbon to carbon, usually black. Let's make bromine red. Chlorine green coming forward. H gray going back. All right. These two are actually eclipsing each other if you hold it like this. I could have drawn this chlorine eclipsing the H. I could have drawn it closer to the H, but this is how it ended up being. Chlorine's forward, H is back. The carbon is over here in the plane of the board. The bromine is straight up in the plane of the board. That's that one. This one over here, bromine is red, correct? Chlorine is green. Chlorine forward, H back, methyl this way, bromine straight. Is that one? Yes. Here are the two. Can you guys see with the light off? Here are the two here. If this looks in the mirror, will it see this? Yeah? You gotta understand this and make sure you see it. So what do we have here? These two are mirror images. Check, they are. Mirror images. But here's a bigger question. Are they the same or different? Are they the same or different? First off, are they isomers? Do they have same formula? Yes. They have same formula. Okay? There's only two types of isomers, constitutional or stereo. Constitutional have different connectivity, thus different names. Do these have same connectivity or different? Same connectivity. A carbon with these things connected. Doesn't matter how it's projected, that's not the same as connectivity. If I put the chlorine on this carbon, then it would have different connectivity than that one. They have the same name. Both of these are this. They're not constitutional isomers. What type of isomers are they? Stereoisomers. Potentially stereoisomers. But are they really? Because maybe they're just the same thing. But we know they're not constitutional. Are these stereoisomers? There's two types of stereoisomers. Enantiomers, which are mirror images. And then diastereomers, which are not mirror images. Don't worry, this is on the next page. There's a big diagram. Enantiomers are mirror images. But are all mirror images enantiomers? You gotta be careful. Everything's got a mirror image. Except for a vampire. But everything's got a mirror image. That does not make them enantiomers. These are mirror images, but are they enantiomers? How do you tell if they're enantiomers? By the way, mirror images that are different. I'm going to go ahead and give the definition and basically say this. Enantiomers are mirror images that are different. And indeed, these are different. And we'll explain why. Just like our hands. Mirror image of this hand is this. I agree? Right? If it looks in the mirror, it'll see that. Okay? Let's take it over here. Are these the same or different? They're different. This is the right hand, this is the left hand. You've known these are different since you were in 4th grade. All right? On the other hand, let's look at these two clips. If this looks in the mirror, what will it see? It'll see that looking back at it. These are mirror images. Yes. Okay. Same or different? These are the same. Which is which? They're the same. Mirror images that are the same, mirror images that are different. These are called enantiomers. These are called the same thing. How do we know when we see something if it's going to be, the mirror image is going to be different or not? Plane of symmetry. Okay? Plane of symmetry. A little bit bigger. If that looks in the mirror, it's going to see this looking back at it. This has a plane of symmetry. You can cut right through there, right in half. Okay? If you can find a plane of symmetry, the mirror image is going to be the same. How about my hand? Does it have a plane of symmetry? Can I cut right through here? No, I'll have a thumb on one side and no thumb on the other. How about here? Can I slice right through here? It's closer, but I'll have a palm on one side, top of the hand on the other. See, if I had palms on both sides, then I could slice right through there and it would be a plane of symmetry. There's no plane of symmetry. That tells me that the mirror image is going to be different. Does this compound have a plane of symmetry? Well, here it is. Let me make sure which is which. Bromine. There it is. This is this one. Does it have a plane of symmetry? Can I slice right through here? No, I'll have half a green on one side, half a gray on the other, but I'll have black on one, red on the other. That's not a plane of symmetry. Well, what about here? I can slice right through red and black, but I'll have green on one side, gray on the other. There's no plane of symmetry. Since there's no plane of symmetry, what does it tell me about the mirror image? It's going to be different. And indeed it is. These two are different. These are called enantiomers. The reason there's no plane of symmetry is because we have a carbon that lacks plane of symmetry. A chiral carbon. The presence of the chiral carbon ruins the whole molecule, ruins the symmetry for the whole molecule if you only have one of them. So if a compound has one chiral carbon, the mirror image is going to be different. Enantiomers. Okay, enantiomers have identical physical properties, such as melting point, boiling point, dipole moment, density, refractive index, on and on and on. Identical. Because it's really the same thing, it's just the compounds that all the oriented groups are just sort of reversed. But if you drew dipole moments here, you get the same thing. They would just be the opposite way on the board, but really the same. Quirk of nature, though. They do rotate plane polarized light in equal but opposite directions. One of them will rotate PP light one way, like to the left, and one of them will rotate PP light to the other way. The one that rotates light to the right, which is the positive direction, is called dextrorotatory. The one that rotates light to the left is called levorotatory. D or L, plus or minus. Left being minus. Okay, we need to do RS. Okay, RS. Please identify these as R or S, because that's how we, this one is R or S. We know how to identify these as left or right. Hold up a hand. That is your left hand. Okay. But when we hold up a molecule, we need to be able to say which one that is. We don't use left or right. We use things like R or S. We can also use D or L, because if we know the rotation information, then we can, okay? By the way, glucose rotates like right. That's why glucose is also sometimes called dextrose. Okay, guys, have a good day.
Yeah, I was like,